At least focus on getting the setup, even if you don't do the actual math. Just get the setup, because we're going to go over these real quickly. See if you've got the setup correct. Still playing with a few things. Went through and reformatted the slides last night, trying to figure out the best place to put the camera. Right now, in the beginning of the course, I've got a lot of the slides, a lot of the math is on the slides. Later on, when we start doing a lot more, I guess you'd say, live work on a blank board, since I don't have a smart board, I try to record as much of that as possible. So I might move the camera more centered and look back, but then at the same time, still trying to reduce the glare. That's a problem as well. So it's not a perfect situation. If I had a smart board, we would just record the smart board writing and put that on the video as well. Don't have that yet. So working on it. So we still are in section 7 of module 1, the more complex unit conversions and problem solving. And if you recall, this is kind of a review, and this would have been a review for the kind of problems you just did, 1.6 through 1.8. When we're converting from a known to an unknown, we kind of changed the vocabulary a little bit yesterday. Remember before it was given and wanted. So if you were absent yesterday, we were kind of moving away from the given and the wanted to the known and the unknown. But whenever we have something in the language of the known and we want to translate it into the language of the unknown, that translation is to put it in different units or to put it in a different form. We use a conversion factor. And do you remember what the conversion factor came from? Just generically, for any problem like this, a conversion factor is going to come from a statement of equality. Something equals something. And when something equals something, then you can make a conversion factor by putting the one side of the equal sign over the other side of the equal sign, in either way. Because the principle, again, is that we're multiplying whatever we start with by 1. It doesn't look 1 because it's different numbers over different numbers, right? And when you do the math, it doesn't equal 1.000. But it's, for example, 1 dozen over 12 pieces. They're the same thing. And so what this is doing is, rather than giving us a different quantity, it's actually kind of translating it into a different language. The language being the language of the units. Remember, any answer that you give that has a number with no units is wrong, because the units are vitally important. The units help us know that we've set the problem up correctly, and when we're asked for something, we need to give an answer in those units. And all we're doing right now really is translating between units. So you can see that the same answer given in 2 different ways has 2 different coefficients, that's the number part, and 2 different units. So we had a known times a coefficient, or excuse me, a conversion factor to give us the unknown. And that conversion factor, we've been setting it up with, okay, I'm given the language of A, whatever units those are, times my desired, my unknown units over my known units gives me my unknown units. Yesterday we added one more wrinkle. We added 2 conversion factors. We went from having 1 statement of equality to requiring 2 statements of equality. And that would look something like this. We used an intermediate term. That's something between, that's going to take us from A to B. If I use those same kind of numbers here, what's my intermediate term? See the formula? A times C over A times B over C equals B. Okay? My given, my known, is A. My unknown or wanted is B. But if I can't translate directly from A to B, I may have to translate from A to C and then from C to B. It would be like, let's say that I spoke English and German, and that you spoke German and French. Okay? And I'm trying to say something to someone in French. I can't do that, but I can say it in German. And you can take what I say in German and change it into French. See? There's that step in between. When we work with Chechen war orphans, it was interesting because we would have a translator who was Somali, who spoke a phonetic Arabic, but he also spoke Russian. So I would speak to him in English. He would take the English and translate it into Russian and speak it to the Chechens. And there were occasionally that I would speak to him in Arabic, and he would take the Arabic and translate it to the Chechens in Russian. But some of the Chechens, because they're Muslim, knew some Arabic, and so they would sometimes hear me directly, but my Arabic was so bad that it was easier for me to go from English to, he would take my English, translate it into Russian, so that the Chechens could understand him. That's kind of what we're doing here. We're taking from one language, changing it to an intermediate language or intermediary language, and then translating it one more time into the language we ultimately want it to be in. That's using 2. We can use 3, 4, 5. We can daisy chain as many conversion factors as we wanted. We could have play that daisy chain game or whatever, you know, where you pass telephone or whatever they call it. You tell the next person something, they pass it along, pass it along, pass it along. You know, pretend that you spoke the language of the person ahead of you and the other language of a person behind you, and I had to start something and we pass it all the way around the room. We would be converting it from one language to another, to another, to another, to another, to another, and just keep translating it all the way along, hopefully saying the same thing. Now, the fun of that game is you realize at the end, people hear something different than you think you say, and so it changes along the way, and there's always some joker that decides they're going to mess up the message. I don't know who that would be in here, but somebody would mess up the message. So that's the idea. That's what we're doing. And On Your Own's 1, 6, 7, and 8 were designed to help you start to see this idea of using multiple conversion factors in solutions. So let's go ahead and look at 106. 106 on page 14 says a balloon is blown up so that its volume is 1,500 milliliters. What is its volume in kiloliters? So what is my known? Right, my volume is 1,500 milliliters. And my unknown? Ma'am? Want the volume in kiloliters, right? So I need something that's going to take me from the language of milliliters to the language of kiloliters. Now, you may know that one off the top of your head, but most people don't. But we do know a couple of statements of equality that take us from milliliters to something, and then from something to kiloliters, right? So what are those statements of equality, sir? That's true. We're working in volume, though, right? So liters. So let's take that as 1 milliliter is equal to 1/1000th of a liter, right? We learned that the milli is 1/1000th. So keep it in this form. 1 milliliter is 1/1000th of a liter. That's going to take me from the language of milliliters into the language of liters. Is that the language I want to translate it into? No. I wanted it in the language of kiloliters. So I need another statement that's going to take me from liters to kiloliters. And that's that 1 kiloliter is 1,000 liters. So see, if I daisy chain these things, I start with milliliters, and this will help me get from milliliters to liters, and then this will get me from liters to kiloliters. Now I can translate from milliliters to kiloliters by using those 2 steps, those 2 statements of equality. So what does that look like? Well, my known was 1,500 milliliters. I'm going to take my 1,500 milliliters and translate it into liters by using this statement of equality with liters over milliliters. Remember, I want what I'm trying to get rid of in the denominator, and the numerator is going to have the units that are in my intermediary units. So this takes it from milliliters to liters. At this point, my units are liters, but that's not enough. I need to get all the way to kiloliters. So I take the second statement of equality and form a second conversion factor with my desired units in the numerator. So 1 kiloliter is equal to, and I divide it by, 1,000 liters. So the units, milliliters cancel milliliters, liters cancel liters. I'm left with kiloliters in the numerator. Am I asked for kiloliters? I am. So my units are correct. Now I invest the time to calculate the actual number. And we had there 0.0015 kiloliters. One 7 asks, if the length of a race car track is 2.0 kilometers, what is it in centimeters? Now, right here, I just want you to stop for a second and think about scale. If I have a distance that's in kilometers, and I'm changing it to a scale, the units of centimeters, Is a centimeter smaller or larger than a kilometer? It's much smaller, right? Since my unit is much smaller, the number must be much larger, okay? Because if I have something in a large scale, that same distance is worth a lot more of a smaller scale. So it's kind of the same idea when we get into scientific notation. I can have a large coefficient times 10 to a small number, or I can have a really small coefficient times 10 to a large number, and they could be the same thing. So we're going from in this case, we're going from 2 kilometers to how many centimeters? Since I'm going from a large scale unit to a small scale unit, my number has to go from a small number to a large number, since they're equal. So, my statements of equality, I start in the language of kilometers. I'm going to the language of centimeters. What's going to be my intermediary unit? Go ahead. Meters, right? Your metric system, usually your base unit is going to be the key. Go to your base unit. So kilometers, centimeters, the middle base unit is meters. So what can I say that relates kilometers to meters? That 1 kilometer is worth 1,000 meters. They're equal. And next, meters and centimeters. Well, 1 centimeter is 1/100th of a meter. You can see that this is going to help me form conversion factors. They're going to take me from kilometers to meters, and then from meters to centimeters. So here's the setup. 2 kilometers, daisy chaining 2 conversion factors. Again, remember these are on your own, so these are all written out in your text, in your answer key in the back of the module. But 2 kilometers times a conversion factor that's going to take me from the language of kilometers and put me into the language of meters. Form that conversion factor from the statement of equality that 1,000 meters is equal to 1 kilometer. Okay? So I start with kilometers. I need meters over kilometers. At this point, I would be in the language of meters. That's not good enough. I need to go from the language of meters into the language of centimeters. So I need another conversion factor that relates 1 centimeter is equal to 1/100th of a meter. So checking the units, at this point, working from left to right, here my units would be kilometers. When I multiply it by meters over kilometers, my units are now meters. And then when I multiply it by centimeters over meters, my units are centimeters. And that's the answer that I've been asked for. Now I would go through and do 2 times 1,000 divided by 1/100th for an answer of 200,000 centimeters. Now, if we did this in scientific notation, it would be a lot more straightforward, right? Because all you're doing is moving the decimal place, from 2 to 200,000. Represents a move of 5, which makes sense. 3 and 2 is 5. So it's kind of a way you can go back and check that. So 200,000 centimeters is the equivalent of 2 kilometers. Remember, 2, small number, kilometers, large scale unit, equals 200,000, many of a centimeter, small scale unit. They're equal. And lastly, 1/8. How many milligrams are in 0.01 megagrams? Now, if someone came to me and asked, aren't they the same thing? No, they're not. Lowercase mg is not the same as uppercase m, lowercase g. 2 different units. And it's not megaman, okay? It's megagrams. So, get out of here. So what, on 1.8, my known mass is 0.1 megagrams. And I need to find out how many milligrams is the equivalent. So again, I'm assuming I don't know anything that's going to take me directly from megagrams to milligrams. If you know this many megagrams equals this many milligrams, you could use that as one single conversion factor, but most people don't. Most of the time, we're going to need some other step in between. And again, because it's metric, I would encourage you to go to the base unit. What is the base unit for megagrams and milligrams? Grams, right? Because of the prefixes, we can very quickly come up with statements of equality and use that for the conversions. So, my statements of equality include that 1 megagram is equal to 1 million grams. And that 1 milligram is equal to 1/1000th of a gram. Knowing those two statements of equality, I can now create two conversion factors to translate from the language of megagrams to the language of milligrams. It's kind of long here, but 0.01 megagrams times, I'm going to my base unit, so my base, or my intermediary unit, which is my base unit, 1 million grams per 1 megagram. See that they're equal to each other. I'm going from mega, so I put mega in the denominator, and in the numerator I have grams, which is my intermediary unit, times another conversion factor based on my second statement of equality, that 1 milligram is equal to 1/1000th of a gram. And the same thing, I'm going to put my intermediary unit in the denominator and my desired units in the numerator. Just using that statement of equality and putting it in the right order. Again, if you go through and the units don't all cancel out appropriately, you know you've got one of your conversion factors upside down. So go back and fix it. We'll talk about that when we talk about derived units in just a moment, so that'll make a little bit more sense. But anyway, this is the setup to translate from the language of megagrams into the language of milligrams. And 0.01 megagrams is equal to 10 million milligrams. All right? Now, this next section, section 8 of Module 1, the area of derived units, and this hopefully will help you a little bit more with what I've been doing in terms of the units. Like we've been talking about mega to gram, gram to milli, so that we end up with millis. When we think about derived units, we're going to consider derived units just like we consider algebra, which you're all awesome at, right? Because you're, just so you know, next year, physics, if you're in pre-calc, you're also going to be initially scheduled in physics. This year, pre-calc has physics and algebra 3. Sing it next door. Anyway, no, I'm kidding. So consider algebra just for a minute. Let's think about this for a minute. Think of the units like you would the variables. For example, here in the book, and these are from your book. I'm just kind of reinforcing what the book has already taught you if you've read up to where we're at now. You should always have read up to, really, you've read past what we've done in class. Read a little ahead of where we are so that you're comfortable when I do it in class for the first time. So this section here, it says 3x times 4y. Now hopefully you would all say, yes, that's 12xy. You see that? Do the coefficients. 4 times 3 is 12. X times y is xy. So it's 12xy for algebra. Now, think of the units in chemistry like you would the variables in algebra. So, 3 kilograms times 4 milliliters equals 12 kilogram milliliters. What is a kilogram milliliter? Have you ever heard of such a thing? How many people in here think such a thing exists? Here's the deal. It does, because you just created it. You just derived it. Okay? Now, if your question says solve for kiloliters and your answer is in the units of kilogram milliliters, your setup is wrong somewhere. Okay? You're going to carry the units just as you would variables in algebra. So in chemistry, this is true. 3 kilograms times 4 milliliters equals 12 kilogram milliliters. Now, this may be an intermediate step in your calculation. Let's say that you've got this formula that you're going to be working. It has 6 or 7 steps. Maybe the next step is going to be divide that by the mass. Well, if you divide that by mass, what are you going to be left with? A volume. Okay? If I divide that by kilograms, I'll be left with milliliters all alone. And maybe my question says, what would be the volume of this thing? So this could be right as an intermediary step. But the units, they're correct because they're derived units. They don't really exist as something we commonly measure, we commonly look at, but they do exist because that is the right answer for this equation. There is such a thing as kilogram milliliters, because when you multiply kilograms times milliliters, you derive kilogram milliliters. Then again, the next step might resolve that into something that we can deal with because we're familiar with it, we're used to dealing with it. That's the whole idea of deriving units. How do we get to kilogram milliliters? If I have a unit that's a kilogram milliliter, I know somewhere you multiplied a volume by a mass. Now, that may have been an appropriate step or it may not have been. Okay? But again, this will help you. If you did this step correctly, and there's another step after this that gives you the next derived unit, that might very well be the appropriate unit for the final answer. So this is a legitimate unit, a kilogram milliliter, because it's a derived unit. In the same way, just as we do division, hopefully you can see here that 6x divided by 2y, well, 6 divided by 2 is 3, and x divided by y is x divided by y. Okay? In the same way in chemistry, 6 grams divided by 2 milliliters equals, oh, that's a typo. I'll go back and fix that. That should be equals 3 grams per milliliter. 3 grams divided by milliliters. That's what should be there. Okay? So, 3 grams per milliliter. Well, a grams per milliliter is a derived unit, but it actually is something we use in chemistry. It's called density. Grams per milliliter is density. So later on we talk about density. The symbol is a rho, one Greek symbol rho. When we write a rho, what is the density? You would take the mass divided by the volume and get a unit of grams per milliliter. And that's legitimate, but it's a derived unit because it involves doing an algebraic step of dividing some mass by some volume. All right? So that's derived units. How do we get them? We handle the units just as we would variables in algebra. So we do the units, in this case, multiplying units or dividing units. We do the same thing. We can go through and do the coefficients, all the numbers in front, and reduce all that down to one answer, one number. You know, this number times this number divided by that number times this number divided by that number. Do the algebra right, you'll get a coefficient that's correct. What about the units? Well, you need to look at the units, go through, and then carry the units to the end. They may resolve out. You think you're done and you're supposed to solve for volume, and your units are a volume unit, you're good. You're supposed to solve for volume, and at the end you've got a mass times a volume. You missed a step. You forgot something. You need to go do something else to it, because your units will resolve to be the correct units if your setup is correct to solve the problem that's asked. Let's go ahead and apply this idea. In the book, it talks about converting 5.208 cubic centimeters to cubic meters. So our known is that we have 5.208 cubic centimeters. The unknown is how many cubic meters is this? Okay. Now, we're translating languages, right? What are if using that terminology that I use, we're translating from the language of centimeters cubed into the language of meters cubed, right? Now, does anybody in here know a statement of equality that can translate directly between centimeters cubed and meters cubed? We're pretty comfortable with centimeters to meters, right? But not so much with centimeters cubed to meters cubed. We do know that 1 centimeter is equal to 1/100th of a meter. That's fine. But if I use that, I need to remember that I need to use it in a very particular way. And you should have done this in algebra, but we'll review it here in chemistry. Notice if I say, and it dropped my formatting again, it does that occasionally. This should be an uppercase, or a superscripted 3. So 5.208 cubic centimeters times, well, my statement of equality is, you know, 0.01 meters over 1 centimeter. That's what I know. When I do the math, I actually get 0.05208 centimeters squared meters. See, because this was centimeters cubed divided by 1 centimeter, that gives me centimeters squared. But I have the meter on top that's not resolved. If I do that same thing 2 times, centimeters cubed times meter over centimeters, meters over centimeters, now my units, my coefficient over there, see how small it's getting? And my unit is centimeters times meters squared. What's that telling me? I got to get rid of centimeters one more time, and I need 1 more meters in the numerator. So the appropriate way to solve this is to do it 3 times across. See that? Centimeters cubed times the conversion factor of meters per centimeter, that would give me centimeters squared meters, times meters per centimeter, that will give me centimeters meters squared, times meters over centimeters, which gives me cubic meters. Okay. I was asked to go from centimeters cubed to meters cubed, and units showed me that I needed to do it 3 times to get the units to be right. Then I go through and actually do the math. Yes, sir?
So could you do that off the bat if you knew it was cubed?
If you knew it was cubed, you could take this, cube the numerator, over cube the denominator. That would give you something over 1, so it's still going to be the numerator cubed. The units would be meters cubed over centimeters cubed, and you could do it as 1 conversion factor. Yes, you could. Matter of fact, in the book, they do that. They show you that method. If you refer over to if you look on the top of page 17, they show it as a 1-step conversion factor. You see, you've got 0.000001 meters cubed over 1 centimeter cubed. That is 0.01 times 0.01 times 0.01 over 1 cubed, which is 1. So you could do it as 1, but you have to remember to cube it, not just do it 1 time. You would know that you were wrong doing the coefficients if you did the unit check. Because see on the top there, you're going to have the wrong units. The second one, you're going to have the wrong units. The third one, those are the right units. Okay, I need to multiply it out 3 times. In your book on example 1.4, we're going to walk through that one as well. It's on page 17. The problem states that the length, width, and height of a small box are measured to be 1.1, 3.2, and 4.6 inches respectively. What is the box's volume in liters? Okay. So our known 1.1 inches, 3.2 inches, and 4.6 inches are the distances or the lengths of each of the sides of the box. And we need to know what is the volume of the box in liters. We're going to need a formula, aren't we? We need to figure out the volume based upon the dimensions. So hopefully you remember that the formula we need is that the volume is equal to the length times the width times the height. If we do that, if we take the formula and actually multiply it out, the volume of the box, I want you to get comfortable with this nomenclature up here. This is how we write this. The volume, this is a general formula for the volume, right? Volume equals length times width times height. Now, when I apply that formula to something that I'm working on, in this case, the box, generally speaking, volume is equal to that. More specifically, the volume of the box that I'm dealing with is equal to that, okay? So you might, later on when we are doing problems where we're comparing 2 or 3 things and we're using the same formula for 2 or 3 different things, you got to keep straight, okay, which piece am I talking about? If there's a box and a ball, the volume of the box and the volume of the ball, you got to keep your measurements straight so you can compare them. So that's why we use a subscripted to tell us what it is. Volume of the box. The volume of the box in this case is equal to the length times the width times the height. I went ahead and wrote inches cubed because hopefully you see that an inch times an inch times an inch is inches cubed. Just like x times x times x would be x cubed. Inches times inches times inches is inches cubed. Cubed tells me it's a volume. Inches is a distance. So it's going from being like measured with a ruler to being measured in a space, three-dimensional space. That's what's happening here. So the volume of the box is going to be those things multiplied out, 16.192 cubic inches. Okay? So now we know the box volume in cubic inches. Was I asked for the volume in cubic inches? No. I was asked for the volume in liters. So now I need to take the cubic inches that I've computed and resolve it out for the appropriate units. So I need a statement of equality. I'm going to go ahead and offer these to you now, but you'll be able to quickly, figure these out for yourself. Think about it. I'm going from inches to, I'm changing units to liters. What strikes you first about inches to liters? Pardon? Well, inches cubed. Let me just do that one. We're going from inches cubed. I misspoke. Inches cubed to liters. They're both volume. Okay? Do you see that we're going to change systems? Okay, so we're going to go from English system, uses inches, to metric system, which is in liters. So I need something that's going to translate me from English to metric. And remember the table? I think it's 1.3 in the book. You can pull out in a statement of equality there that 1 inch is equal to 2.54 centimeters. That's going to be my hook to get me, that's my bridge rather, that's going to get me from English units into metric units. So I need something, some statement of equality that's going to move me from one unit system to the other unit system. And I know that if I have that key, I can take it from this unit system of inches cubed and somehow eventually get it into the metric system of liters, because I have an equality that takes me from one system to the other. I may know what a cubic inch is worth in liters. If I did, that'd be a shortcut. Right now I don't. But I can get from a length unit of inches to a length unit of centimeters. So I also know that eventually I want it to be in the language of cubic liters. I don't know necessarily what that is now, what the conversion factor is, but I do know that milliliters are related to liters in this way, right? And even though this is a distance and this is a volume, I'm going to need a third key, something that's going to convert from a distance unit to a volume unit. Now here's the key, and this key, you're going to use it repeatedly in this class, so you've got to know this one. This is up here almost all the time for these type of problems. The fact that, and in your book it's in blue, I put it in blue in the slide, that 1 cubic centimeter is equal to 1 milliliter. 1 cubic centimeter, it's abbreviated cm superscripted 3 for a cm cubed, cubic centimeter. It's also occasionally referred to as a cc. Like you're watching those doctor shows, give them 12 cc's of whatever. It's 12 cubic centimeters. They could just as easily have said, give them 12 milliliters. They're the same thing. A milliliter is a volume unit. A cubic centimeter is a distance unit times a distance unit times a distance unit, which is a volume unit. And that is the definition of a milliliter. A milliliter is 1 cubic centimeters worth of stuff, specifically water. So this is the key to translate between a distance unit and a volume unit in the metric system. So those are the 3 statements of equality that we're going to use to go from cubic inches to liters. And here's how it plays out. Okay, I know my volume of the box is 16.192 cubic inches. And I have something that's going to take me from centimeters to inches and back and forth, but I can't do it just one time, can I? We just learned I've got to do it 3 times because of the cubing effect. So I do it 3 times, and that gives me an answer. Well, here it is. I went through and rewrote it as that same unit 3 times. That's just as legitimate. This times itself is the same as writing this cubed. Equally true. They're the same thing. That's going to give me, over here, see if I did this cubing, if I took 2.54 times 2.54 times 2.54 over 1 times 1 times 1, it would give me this. So like Zach referred to earlier, I could do this as one simple conversion factor if I cube the numerator and cube the denominator, resolve out the coefficients and keep the units, and you can see I can translate from inches cubed directly to centimeters cubed by that last statement there. And that's going to give us 265.338 cubic centimeters. Again, this is all in your book. You can review this in the book. So what have I just done? I've translated from the language of cubic inches into the language of cubic centimeters. Is that what I was asked for? No. Okay, so there's more steps I need to do. So now I know that the volume in cubic centimeters is that number. I need to apply another statement of equality that we had over there, that 1 milliliter is the same as 1 centimeter cubed, right? A centimeter cubed. My units are centimeters cubed. Notice in my conversion factor, the denominator is centimeters cubed. That means they're going to cancel each other out. When they cancel each other out, what am I going to be left with? Units of milliliters. And that's what we have right here. So 265.338 cubic centimeters, I could say that another way. I could say that as 265.338 milliliters. Was I asked for milliliters? No, so I'm not done yet. Now I need to go from milliliters to liters. We do that with our final statement of equality, creating the conversion factor. Here's my milliliters times 1/1000th of a liter is equal to 1 milliliter. Milliliters cancel milliliters. I'm left with liters. That's what I'm looking for. And when I do the math, I have 0.265338 liters. So all of that, 16.192 cubic inches equals 0.265338 liters. I was asked for liters. I have it in liters. I'm done. So that is the multi-step process of going from, in this case, length units in the English system to then create volume units, still using the English system, converting the length units in the English system, or the volume units in the English system, to the volume units in the metric system, using that key, then changing the units in the metric system to the requested units in the metric system. So it's a multi-step process. If you understand the process, you just apply it basically 3 different times. Remembering that if something is squared, you can't convert it one time. You can't use one conversion factor. You've got to square the conversion factor. If it's cubed, you can't use the conversion factor one time. You have to cube the conversion factor. Okay? I know there might be some algebraic question on that, okay? But that really is an algebra question, and we can deal with that more. And the best way for you to get it is to practice it and get it right. It's the only way to really learn it. So we're going to go ahead and finish with this. Review questions 1 through 5 and practice problems 1 through 4. You can work on it on your own. Right now, this is homework due on Thursday. So you can get a head start on that.